Clocking has been a topic of the multi-vendor interoperability event for a long time, for many years actually. I don't even want to let you know when we started, but we have rarely been able to demonstrate clocking live because in the old times the clocks took hours to synchronize and to stabilize, and then we needed, one year we ran a cable to outside, so to have a satellite view of the sky, and all of these challenges have been overcome by modern technology. So I'm really happy to introduce this demo. And because there are so many vendors lining up, I think we have 8 vendors in total, of which 4 or 5 are going to speak. I don't want to waste your time. So over to Neil Jackson from Calnex, who's the first of the speakers.
Thanks, Karsten. Hi, as Karsten says, I'm Neil from Calnex, and today we're going to be talking in the second clock synchronization demo about a chain of Class D boundary clocks. If you saw the first demo yesterday, we showed synchronization there as well, along with a number of other new features, new functionalities, as Karsten mentioned, things like passive port monitoring, where we can identify asymmetry in the networks and potentially compensate for that. We had a 400 gig tunable optics link in there as well, so we showed timing performance over there. And we also had some interworking function, converting between full timing support and partial timing support profiles. And all of these are kind of like new developments, new capabilities within synchronization. Today we're going to take a little step back really and show something a little bit simpler, which should be easier to demonstrate, and I'm hoping we've actually got it running now, hence the little panic earlier. So, what am I doing here? Okay, so today we have a chain of boundary clocks and we're going to be measuring them as well. So we've got the same test equipment as we had yesterday. We have Cyantan from Keysight, who will show some of the results from the time sync analyzer later. So they're doing multiple measurements across nodes in our chain to show how time error is actually accumulating through the network. And we're also going to use the Calnex Paragon Neo to look at the initial time error from the first hop in the chain and how compare that to the result at the end of the chain of boundary clocks. In the order the chain is actually composed, we have a number of routers here. I'm not going to talk about them in any great detail because I can't, but the guys here will be more than happy to share any details if you're interested, and come and find them. They can give you more information, follow up afterwards. So at the head of the chain we have devices from Cisco, Huawei and Arista. In the middle we've got Juniper, Ciena and Ericsson. And then at the end of the chain we have ZTE, H3C and microchip devices. And all of these are configured as Class D boundary clocks using G8275.1 profile and obviously SyncE. Because these are Class D devices, we need to use enhanced SyncE in this chain. Okay? That brings some considerations of its own. So what we've got here is an overview of the topology, some of the details that we're going to go into in a little bit more depth in a few seconds. But before we get into that, I'm going to hand over to Dennis from Cisco, who's going to explain some of the intricacies of how enhanced SyncE works.
Thanks, Neil. So there's 2 basic components to enhanced synchronous Ethernet. The first thing is the actual performance of the clock itself and being able to maximize the performance. The other thing that needs to work for synchronous Ethernet is the enhanced TLV. So this is an enhancement that was made to the quality level messaging that is sent through a SyncE network. And so we have to have both of those in place to have a chain of enhanced synchronous Ethernet. But what I want to show you here is this capability also has backward compatibility built into it. So the chain of clocks we have here today, there's actually 1 or 2 clocks in the chain that is not forwarding the enhanced TLV on. So what I wanted to do is just show you quickly how this works. With the enhanced TLV, we have the ability to have the new quality levels which are being introduced by the ITU-T, things like enhanced DEC, enhanced PRC and so forth. But what happens is we've also introduced some new capabilities into this enhanced TLV, similar to the PTP announce message. And this is things like a hop count, so we can tell how many hops it is from the reference, and also a clock identity. At the moment, there's not really any mechanism in the standards to use those values, but that should be coming. What it will do is when a SyncE clock sees these new TLVs, if it supports the new TLVs, then it will take the highest level clock. So there is an order of clock. It will pick an enhanced one over a non-enhanced one. So I have an example here. I'm not going to go through it all in detail, but if you're interested, you can have a look at the slide later. But one of the things we're showing here is that the backward compatibility. So that the node in the middle here is a legacy clock. When I can find my mouse. So here we have a legacy clock, right? And it's just a standard SyncE clock, and it doesn't support the enhanced TLV. So what it does is it drops it, right? And this is secret to the backward compatibility. So it just sends on the standard TLV saying it's linked to PRC, and the next clock in the chain, being an enhanced SyncE clock, will actually recreate the enhanced TLV, and it will set a flag to say that there's been a break in the chain somewhere. So with this mechanism, you still get the SyncE performance where you have it available in the enhanced clocks, but you can still recover the messaging by having this backward compatibility. Okay, with that, the only thing I'll show you really from my point of view, I'm the first clock in the chain. You can see that I have, right, I'm getting ePRC from the grandmaster, right? So this is an enhanced TLV, and I'm passing it on downstream. If you look at the PTP, I've got a 100 gig port, which is in a slave state, connected to the grandmaster. So I'm receiving clock class 6 and ePRC from then. What I also have, just revisiting what we were doing yesterday, we also have passive port monitoring. So I have a connection to the Ciena, which is about 3 hops further down the chain, and I can actually see what offset is coming to me from the Ciena. So passive port monitoring is monitoring the timestamps from the Ciena, and I can calculate that we see about 16 nanoseconds offset after 3 hops down the train. Okay, that's all I have to cover, so I'll hand you over to Bjorna from Juniper. Thank you.
Thank you, Dennis. So, my name is Bjornar from Juniper. So, I'm going to show you a few commands to really prove the chain on the boundary clock, to really see that we are locked to the SyncE and the PTP information throughout the chain. So, this is shown actually through the ACX device. So if we start with the SyncE, you see that the clock event is clock lock. So we are locked on the SyncE. So it means fine on the SyncE side frequency, we are good. So if we go for the next thing to check, is to really check the PTP. So you see that we are phase aligned over the 100 gig, the ET100. And to really prove that we are running in the hybrid mode, that has been discussed earlier, you see that the clock state here is frequency locked and phase locked. So we are locked both on the PTP and the SyncE in the hybrid mode. And we are down the chain here. And if you look on the clock detail here, you see this grandmaster ID starting with 0011, ending at the 02. That is really the grandmaster ID of the Keysight. And the parent ID you see, starting with 60, ending at 1D, is the Arista boundary clock upstream to me, upstream master. So it just proves that we see the grandmaster, we see the upstream, and so like this you can actually follow the chain here. And with the last command I would like to see, this is just the all master clock which I'm proving to see what I'm seeing. I just have one interface here, so you just see one set of interface. But this is what Arista is sending down to me. So if I had 2 interfaces, we would actually see 2 kind of information set like we had in the demo yesterday. So that's what I wanted to show from the Juniper device. So I hand over to Felix from HTC.
Thank you. Hello, good afternoon. My name is Felix from S3C. Maybe this name is not so familiar to you guys. But if you Google it, you will find a very interesting, history the relationship with Cisco's, HPE, and 3Com. Today, I'm going to briefly introduce what we did for EANTC. Because this is the first time S3C joined this interoperability test, and we proposed our the very slim core router, which is just 2U high, and but this is a very reliable router. First, you can see it has 2 redundancy control plane on it. And in the middle, it has 2 powerful line card, which can adapt, 100 giga, 400 giga, and also it's also very flexible. It can divide the whole line card to sub-interface to line card, and which is more scalable for the future use, And for the testing, you can see we put into the chain, and our upstream is Ericsson routers, and our downstream is ZTE, and we configured the proper PTP profile together, and also we did the enhanced, as mentioned by Cisco, we provided the enhanced synchronized E. And also the downstream, we are very flexible. We can configure 2-step as well as 1-step, the profiles to be more flexible, to backward and compatible with the different profiles. And the result is also very positive. The offset is within 1 nanosecond. So this is what we did for these test cases. Thank you, guys. If you have any questions, you can visit our booth. We are very welcome to answer any questions. I will hand over to Neil.
Okay. Thanks, Felix. Okay, so we've seen from the device vendors what they're reporting on their devices. Now we're going to have a look at the test equipment to determine time error and the status of those devices matches what we've seen. So the first thing we want to look at is our SyncE status. And what we can see here is, as per Dennis's description of what the Cisco device is seeing, we're getting EPRC as an output from that device, showing that that device is locked to the upstream SyncE reference, and it's passing that full enhanced TLV downstream. So we're maintaining that enhanced synchronous Ethernet chain through the network. And we can see by looking at the actual frequency error or time error measurement, time interval error measurement on the SyncE, we're bang on, absolutely aligned there. So we've got very good performance going into the network. If we then look at the other end, so where we're actually taking that last node in the chain, we can see we've dropped down to PRC here. And this ties in with what Dennis was explaining about the backwards compatibility, where you may have a node that understands EPRC on its input, but doesn't transmit that enhanced TLV downstream. But by looking at the tie error on the last node, we can see we've still got a very good frequency reference there. So we're still maintaining that high stability despite not actually supporting the enhanced TLV through the whole network. If we then look at our time error at the start and end of the chain, we can see at the bottom we're within a nanosecond of time error relative to the grandmaster. And at the end of the chain, we're currently just under 16 nanoseconds misaligned. So across a chain of 9 devices, as per the topology, that's a pretty good result. And we can confirm that by looking at the relative time error in real time between these measurements. And we can see we're currently averaging just under 17 nanoseconds. So this ties in quite nicely with the point that we make on the slide here. Whereas one of the challenges that we had with this test is, what do we actually expect as a time error result? So these are Class D devices. There's only a single metric defined, and there's no definition within the ITU-T recommendations for how that time error actually accumulates. So we had a bit of a discussion, and we decided there were 2 extremes. Either we could consider that it's a constant time error allowance, the entire budget is taken up by an offset effectively, and that means that would scale linearly through the network. So you've got 9 devices, you've got 9 times 5 nanoseconds as an error. We've got 10 here because that's what we did in Berlin, slightly shorter today. The other extreme is to consider that it's all dynamic time error. So it's highly variable. It doesn't scale linearly. It scales as the root of the sum of the squares of the individual values, which means for 10 nodes it would be about 16 nanoseconds. So our chain today is slightly shorter, but you can see it's erring more towards dynamic time error than constant. And that's great. That ties in with how it should be really, because a constant time error is something that you can measure, you can compensate for. Dynamic, you can't. Okay? So the results today tie in with the concepts of what we expect from this time error. But what we'd also like to see is the results through the chain to understand, is it accumulating in a way that makes sense compared to the overall? Is it variable? Or is it just summing linearly and coinciding? So I'm going to hand over to Sayatan from Keysight, who's going to show some results within the network to show that accumulation.
Thank you, Neil. Hi, good afternoon, everyone. I'm Sayatan, and I'm from Keysight. And now I'm going to explain to you Keysight's time sync analyzer's role in this topology. So let me switch to Keysight time sync analyzer UI. So it's playing dual role here. So one role is that one role it is playing is the reference. It's providing PTP and SyncE as time and frequency reference to the Cisco, which is the first boundary clock in the chain. And then it's also measuring the intermediate boundary clocks in the chain. For example, the time synchronizer is connected to hop 2, which is from Huawei, and then at hop 4, which is the boundary clock from Juniper, and then Ericsson, who is hop 6, H3C, and ZTE. So now I'm going to show you the measurement across few of these nodes, 3 nodes actually. So for that, let me go and start the measurement first. So my measurement is started, and first thing we are going to look at is the SyncE time interval error performance. And to have a comparative view, I have basically combined view of the time interval error from Huawei, Juniper, and Ericsson. And you can't really, differentiate one from the other. So, and if you look at the max and mean, probably, all of them are within plus minus 0.2 nanoseconds. So it just shows, the capability of SyncE to deliver the frequency, almost undisturbed to the end of the chain. And then let's have a look at the PTP time error across these 3 devices. Okay, now you see 3 graphs. The purple one is the Huawei boundary clock, which is showing about 2 to minus 2 nanosecond. And since it is hop 2, it is much closer to the grandmaster, right? And it explains why it is better, right? And then we look at 2 others. So the blue one here is the Ericsson, which is at hop 6, and then we have Juniper at hop 4, and they are very close to each other, right? And we can see that there are some constant time error accumulated through the chain towards the end of the chain. And that's what is reflected in the time error measurement of Juniper and Ericsson devices. But still, if you see, it is within 16 nanosecond, which is actually matching Neil's measurement of relative time error across the first hop and the last hop, which is around 16 nanosecond, just about same. So with that, I would like to hand over to Neil for his concluding remarks. Thank you.
Okay, sorry, Carson. 30 seconds just to wrap it up. So as you can see, today we've managed to successfully get a chain of devices interoperating. We've proved that the clock synchronization, both for PTP and for SyncE, has passed successfully. And as Carsten mentioned earlier, we're achieving performance that we possibly wouldn't have imagined even a few years ago. So thanks to everyone for your help putting the chains together. Thanks to Carsten for hosting everything. And I'll hand back over. Thank you.